So, we've spent a while trying to understand various kinds of motion, right? And when we spoke of motion, we were focusing ourselves on the position, velocity, and acceleration of a particle. But we never investigated what caused that motion. We never investigated what caused that motion. Now, what we would look at, so essentially what we have looked at so far is jugglery between two entities, length and time. See, all velocity, acceleration, etc. Position, they were about length and time. Two fundamental quantities, length and time. Now, we migrate into a domain where mass becomes important. So now it would be about mass, length and time coming together in various ways and creating various concoctions for us. Now, so like I said, we have not yet looked into what causes motion, right? So what we start doing is, we start this journey by defining another entity for us. If a particle has a velocity v and has a mass m, if a particle has a velocity v and has mass m, then we define the linear momentum of this particle p as mass into velocity. Mass into velocity. Mass is a scalar, velocity is a vector. Very clearly, the direction of p is the same as the direction of v. Direction of p is the same as direction of v. So this is linear momentum. Now, obviously, p and v are parallel to each other. Now, how would p change? P would change every time v changes, right? P changes when v changes. Now, when would a vector change? V is a velocity vector. When would it change? Either its magnitude changes, or its direction changes, or both change, right? V changes owing to the following reasons: change of magnitude, change of direction, and change of magnitude and direction. Right? Change of magnitude plus direction. Say, for example, if a particle is moving along this line with a velocity of 3 meters per second, right? After a while, its velocity becomes 6 meters per second. This is only change of magnitude. This is only change of magnitude. I could have had a particle moving in this direction with a velocity of 3 meters per second, speed 3 meters per second. After a while, its speed becomes 3 meters per second like this. So only the direction changes, but the speed remains the same, magnitude remains the same. Or we could have had a particle moving, say, with a velocity of 3 meters per second. After a while, it starts to move in this direction with a velocity of 6 meters per second. In this case, both the magnitude and direction has changed. In this case, both the magnitude and direction would have changed. And change of velocity, like I said, is characterized by acceleration. Change of velocity is characterized by acceleration. You understand that acceleration is dv dt. Acceleration is dv dt. Rate at which velocity changes, that is acceleration. Now, say in this case, let me say this was the x direction and this was the y direction, right? What was the initial velocity vector? Can you tell me? 3i cap. 3i cap was the initial velocity vector. When this happens, what's the velocity vector? 3j cap. 3j cap. Now, what's the change in velocity? Change in velocity is final velocity v2 minus v1. which is 3 into j cap minus I cap. That's a change in velocity in this case, right? In this case, what is the initial velocity v1? 3 I cap. What's the final velocity? 6 I cap. What's the change in velocity in this case? v2 minus v1, which is 3 I cap is the change in velocity in this case. Now, let me look at this case again, this being the x direction, this being the y direction, right? Right. What's the initial velocity vector in this case? 3 I cap. What's the final velocity vector? Can you tell me? It has a component 6 cos theta like this. You can see it has a component 6 cos theta like this, and it has a component 6 sin theta like this. So, what's the final velocity? 6 cos theta I cap plus 6 sin theta j cap. And this will, v2 minus vf minus v1 will give you change in velocity. Yes or no? Now, obviously, you know, these changes could have occurred in a certain time. If I divide the change in velocity by time taken, if I divide the change in velocity by time taken, I get the average acceleration. I get the average acceleration. I get the average acceleration of the particle. Right? Now, what I want to tell you is this linear momentum. If linear momentum is mass into velocity, change in linear momentum would be mass into change in velocity. We will assume that we are dealing with a system that has constant mass. Although that may not always be true. We can have systems of variable mass as well. But to begin with, this journey would be about systems that maintain constant mass, right? Now, whenever, see, a particle has a fundamental property. If there is a mass, m, and it has a velocity v, there is a fundamental property that it has. The fundamental property of a particle or a mass, fundamental property is that it would want to maintain the same velocity. It wants to maintain the same velocity, that means same state of motion. Right? It wants to maintain the same state of motion, means the same velocity. It wants to maintain both magnitude as well as direction. And that property of a mass, by virtue of which it would want to maintain the same state of motion, is called inertia. It's inertia, right? So it would resist change of motion. Resistance to change of motion. And the greater the mass, the greater will be its inertial property. It will resist change of motion even more, right? Now, therefore, to change the velocity or the state of uniform motion of a particle, one would have to do something to the particle. To change the state of motion of a particle, one would have to do something to the particle, because that particle is resisting that change. So you would have to do something to the particle, because its fundamental nature is to maintain its state of uniform motion. So what you do to the particle so that its state of motion can change is called an external force. So what's an external force? An external force is one that in a certain sense goes against the wishes of the particle. Its property of inertia is resisted and it results in change of motion. Otherwise, on its own, the particle is happy to maintain the state of motion it is given, right? To break through that, to break past that, what is done to the particle is defined as the force. A force, therefore, is an entity or an agent or a quantity that resists inertia, that opposes inertia, that causes change of motion, that causes change of velocity of the particle, and therefore that causes change of linear momentum of the particle. So force is then an agent that causes change of motion of the particle, right? We define the force acting on a particle. We define force acting on a particle as rate of change of linear momentum. Rate of change of linear momentum is defined as the force acting on the particle. And this force is measured in what's in SI units referred to as Newton. Newton. Now, P can be written as mass into velocity. P can be written as mass into velocity. Now, m being constant, because we are dealing with systems with constant mass, m comes out of the derivative sign. So, if m comes out of the derivative sign, it's m dv dt. But dv dt is the acceleration brought about in the particle. dv dt is the acceleration brought about in the particle. So, this is m into a. That is m into a. So, that's essentially Newton's second law. F is mass into acceleration. That's Newton's second law. That's second law. Force acting on a particle. So, this is the cause and this is the effect. F is a cause, and you know, the cause of F could be very many. And what's the effect? The effect is the acceleration. This is the cause and this is the effect. So that's Newton's second law. That's Newton's second law. What about the first law? First law is that if there is no external force acting on the particle, if there is no external force acting on the particle, then A is 0, it means V must be constant. Right, that means a particle in absence of a net external force, maintains its state of uniform motion. It moves in the same straight line with the same speed. It maintains its state of uniform motion, constant velocity in absence of an external force, net external force. That's Newton's first law. That's Newton's first law. You've been reading all of this from the time you were kids, right? Again, there could be two particles, m1 and m2. There could be two particles, m1 and m2. And they could exert forces on each other. They could exert forces on each other. Let's say they interact with each other. Whenever I say two particles interact, it means they exert forces on each other. They exert forces on each other. God bless you. Now suppose m1 exerts a force on m2, which is force exerted by 1 on 2. It's like force exerted by 1 on 2. Then Newton's third law states that m2 will exert an equal and opposite force on m1. Then the force that m2 exerts on m1 would be F21, where the two forces, this is the force that 1 exerts on 2, this is the force that 2 exerts on 1. These are forces that they exert on each other. These are forces not acting on the same particle, they are acting on different particles, right? And Newton's third law states that if these two particles interact with each other, they exert forces that are equal in magnitude and opposite in direction. That means if these two forces are equal in magnitude and opposite in direction, that means vectorially they must add up to 0. God bless you. That means F12 plus F21 must be 0. F12 would be minus F21, implying that these forces are equal in magnitude but oppositely directed. Yes or no? Right? So that's essentially Newton's third law, right? Now, suppose there is a particle which falls from a certain height onto the ground. Say it falls from a height h1 equal to 5 meters. It falls from a height h1 equal to 5 meters. It hits the ground. It hits the ground, and obviously it starts from rest, and then eventually it rebounds to a height h2, say equal to 3.2 meters. Say equal to 3.2 meters. Now I want to find that and suppose the time of contact with the ground, there is a small time of contact with the ground. The time of contact with the ground, suppose, was 0.01 seconds. Was 0.01 seconds was the time of contact with the ground. Okay. Very clearly, the particle hits the ground with a certain speed, call it v1. Right? And it rebounds with a speed v2. It rebounds with a speed v2. Right? Now, there is change in linear momentum in the particle. Right? The final linear momentum is, let's say the mass of the particle is 1 kg. Let's say the mass of the particle is 1 kg. The final linear momentum is mv2 upwards. Is the final linear momentum. The initial linear momentum is mv1 downwards. Yes or no? Suppose the upward direction is positive. Now, what is the change in linear momentum? Change in linear momentum in the upward direction. Change in linear momentum in the upward direction. Is like final linear momentum in the upward direction minus initial linear momentum in the upward direction. So, what's the final linear momentum in the upward direction? mv2. Minus initial linear momentum in the upward direction. So, linear momentum in the downward direction is mv1. So, initial linear momentum in the upward direction would be minus mv1. So, final linear momentum in the upward direction minus linear momentum in the upward direction, which is that is change in linear momentum, would be m into v2 plus v1. Yes or no? That's a change in linear momentum, and this change has taken place in the upward direction. Right? The ground must have exerted an upward force on the particle. Right? The ground must have exerted an upward force on the particle, so that there is change in linear momentum in the upward direction. Right? Change in linear momentum takes place in the same direction in which the force acts. Change in linear momentum takes place in the same direction in which the force acts. See, F is dp dt. Yes or no? So, dp is change in linear momentum. F is the force. Very clearly, F and dp must be parallel vectors, because dt is a scalar. Right? F, the force acting, must be parallel to change in linear momentum dp. Change in linear momentum dp. Direction in which the change in linear momentum takes place is the direction in which the force acts. So, in this case, the change in linear momentum has taken place in the upward direction. You can see it's positive. So, the force acting on the particle must have been upwards. And who exerted that force? The ground must have exerted the force. For how long? 0.01 seconds. So, this change in linear momentum took place in what time? In 0.01 seconds. That means the change in linear momentum divided by the change in time taken, that must be the external force acting on the particle. Right? And that must be equal to, say, m into v1 plus v2 divided by delta t. Now, how do you obtain v1? Do you realize when the particle falls from rest through a height h1 equal to 5 meters, the velocity with which it hits the ground, v1, must have been root 2g h1? Yes or no? h1 is 5 meters. So, this is 10 into 10. That makes it 10 meters per second. Yes or no? Now, it starts to go up with a velocity v2 and comes to rest after having traversed a height h2. So I apply between this point and this point, v square minus u squared is 2as, right? So what do I get? 0 squared minus v2 squared is 2 times minus g into h2. h2 is the height that it, yes? So v2 then must be root 2g h2, which is root 2 into 10 into 3.2, which is 8 meters per second. So I can plug in m equal to 1, and v1 plus v2, as you can see, is 18 divided by 0.01. That makes it 1800 newtons must be the force that the ground exerts on the particle to cause this change in linear momentum. 1800 newtons must have been the force that the ground must have exerted on the particle in the upward direction to bring about this change of linear momentum. Now, if the ground exerts on the particle 1800 newtons upwards, what does the particle do to the ground? The particle will exert on it 1800 newtons downward force. 1800 newtons downward force.
If we take it downward as positive.
Right? So far so good. Not an issue. Now, suppose there is a circular tube. Smooth. Now, say there is a particle of mass m equal to 1 kg that enters this tube with a speed of 1 meter per second, like this, right? This, and its speed is maintained constant, and it comes out of this semicircular tube with a leftward speed of 1 meter per second. No, horizontal. And it doesn't matter. Let's say it's on a horizontal ground. Right? So this particle maintains constant speed, but is the linear momentum constant for the particle? No. There is change in linear momentum. Final linear momentum in the leftward direction is m into v. Initial linear momentum is in the rightward direction, which is m into v. So change in linear momentum in the leftward direction. Is what? Final linear momentum in the leftward direction minus initial linear momentum in the leftward direction, right? That's change. So that's final p in the leftward direction minus initial p, means linear momentum in the leftward direction. Yes or no? That's a change in linear momentum in the leftward direction. Now, what's the final p in the leftward direction? M into v. Minus, what's the initial linear momentum in the leftward direction? It's mv in the rightward direction, so minus mv in the leftward direction. So minus mv. So change in linear momentum is 2mv. Right? Now, what's the time taken to bring about this change in linear momentum? Time taken to cover this semicircle? Now this semicircle is of radius r, say. This semicircle is of radius r. So what is the length of the circumference covered? Pi r. Pi r is the distance covered by the particle with a constant speed of v meters per second, right? So time taken would be pi r divided by the constant speed v, isn't it? That's the time taken. So Now if somebody says, what's the average force that the tube exerted on the particle? After all, this change in linear momentum was brought about by the tube. So if somebody says, what was the average force that the tube exerted on the particle, then the average force that the tube exerted on the particle would be the total change in linear momentum, which is leftwards, divided by the time taken. And it will be towards the left because change in linear momentum is leftwards. So the average force that the tube exerted on the particle will also be leftwards. So that's going to be delta P left, which is 2 mv, divided by delta T, which is pi r by v. Pi r by v, that means this. Clear? So far so good. Now, there could be a system of particles that mutually interact. There could be a system of particles that are mutually interacting. Suppose there is a particle m1, there is a particle m1, and there is a particle m2. M2 exerts on M1, M2 exerts on M1, say a force F1. F1 is the force that M2 exerts on M1. And F2 is the force that M1 exerts on M2. On M2. Right? F1 and F2 are forces. F1 is the force acting on M1, and who exerts this force? Say M2. Right? It can be any direction. It can be any direction. How does that matter? I mean, it could also have been like this and like this. That's okay. Okay. And so this is a pair of particles. This is a pair of particles. And say, so these are mutual interactions of the particle. These are mutual interactions of the particle. Now, in addition to mutual interactions, beyond mutual interactions, all the forces that act on M1 or M2 or both, they are external forces. If this is looked upon as my system, if M1 plus M2 is considered to be a system, it's my choice. What I call as a system is my choice. If M1 plus M2 is considered a system, then what they do to each other, F1 and F2 is what they are doing to each other, those forces are called internal forces. Those are internal forces. What they do to each other are internal forces. And all forces, that other forces that are acting on M1 or acting on M2 are external forces, right? So, say there is a force F0 acting on M1, F01 say acting on M1, and there is a force F02 acting on M2. It's possible that one or more could be 0. If F01 could be 0, F02 could be 0, or both could be 0. The particles could be simply moving under the influence of each other's forces. There could also be external forces acting on M1 and M2. For M1 and M2 to be a system, F01 and F02 are external forces acting on the system. F01 and F02 are external forces acting on the system. on the system comprising M1 and M2. Now, doesn't mean that I can't look at M1 and M2 separately. I can look at M1 and M2 separately. Now if I say look at M1 separately, when I say look at M1 separately, it means I'm freeing M1 from M2 for a while. So if I look at M1 separately, this is my M1 and I am examining M1 separately. If you look at M1, then what are the forces acting on M1? There is a F1 like this, and there is F01. I can shift it here, right? I can shift it here. I'm just placing it here. F01. This is the summary of forces acting on M1, right? This is summary of forces acting on M1. On M1. This is summary of forces acting on M1. M1 by itself understands only these two forces. And suppose, so the net force acting on M1 would be the resultant of these two forces? Yes or no? The net force acting on M1 would be the resultant of these two forces, which would be this. This is the net force acting on M1, F net acting on M1. I can find using parallelogram law of vectors the resultant of these two forces. That means if this is the direction of the net forces acting on M1, this must also be the direction of the net acceleration of M1. The acceleration of M1 would be in the direction of the net force acting on M1. The direction of acceleration of M1 would be the same as the direction of the net force acting on M1. That means this. That means the acceleration of M1 would be like this, say A1. So it would be A1. Yes or no? Now, what is this F net is what? Vectorially F1 plus F01, right? So the net force acting on M1, equation of motion, I am applying Newton's second law to M1. I am applying Newton's second law to M1. What is the total force acting on M1? F1 plus F01. That's the net force acting on M1. And what does it do to M1? This is the cause. What's the effect of this cause? A1. That causes on M1 an acceleration A1. That causes on M1 an acceleration A1. Yes or no? Right? So that's equation of motion written for M1 alone. This is the free body diagram of M1. Summary of forces acting on M1 alone is called the free body diagram of M1. This is called the free body diagram of M1, FBD. We refer to this as FBD. Summary of all forces acting on M1. This. And this is the effect of all those forces. This is the effect of all those forces, right? Now, look at M2. Summary of all forces acting on M2. This is M2. Right? F02, let me shift it here. Let me copy and paste, cut and paste this here. So this is like a F02. And there is F2. This is the summary of all forces acting on M2. Yes or no? The net force acting on M2 would be the resultant of these two forces. This is the net force acting on M2. Right? This is the net force acting on M2. F net 2. And if this is the direction of the net force acting on M2, the acceleration of M2 would be in the same direction, A2. The acceleration of M2 would be in this direction. Right? Now, so this is my free body diagram of M2. This is the cause and this is the effect. Alright? Now, if I apply Newton's second law to this, what do I get? F2 plus F02 is M2 into A2. Yes or no? This is free body diagram of M1. This is equation of motion of M1. This is equation of motion of M2. Now, let me add these two equations. F01 and F1 and F2 are mutually interacting forces. F01 and F02 are external forces acting on the system comprising M1 and M2. Let me add equation 1 and equation 2. So when I add equation 1 and equation 2, I get F1 plus F2 plus F01 plus F02 is M1A1 plus M2A2. That's adding equations 1 and 2. Now, F1 and F2 are forces equal in magnitude and opposite in direction. So from Newton's third law, two forces that are equal in magnitude and opposite in direction, vectorially they must add up to 0. F1 plus F2 vectorially must add up to 0. That means if this force is 3 newtons like this must be 3 newtons in the opposite direction. So now this F1 plus F2 will cancel off. This will be 0, right? So this turns out to be 0. And F01 plus F02 is the net external force acting on the system comprising M1 and M2. So this is the net external force, acting on the system of particles comprising M1 and M2. So this F01 plus F02 I designate as F net external acting on the system of particles, SY is system comprising M1 and M2. And what does it do to the system? It gives M1 an acceleration A1 and it gives M2 an acceleration A2. That means if I look at M1 plus M2 as one single system, this is my equation of motion for the system. It does not contain, it hides from you one fact: what they are doing to each other. What they are doing to each other is not expressed and represented in this general statement of equation of motion for the system of particles comprising M1 and M2. These were internal forces. They remain internal. They remain a closely guarded secret for M1 and M2. You are an external agent. You apply a thrust on these particles in the form of external forces. And they tell you, all right, M1 receives an acceleration A1, M2 receives an acceleration A2. Although A1 and A2, A1 is the resultant of not only just the external force but also the mutual interaction. A2 is also an outcome of the internal force and external force, but M1A1 plus M2A2 does not reveal the internal forces. When they get added up, they cancel up the internal forces, they settle matters between each other, and they only provide to the outside agent the net effect A1 and A2. They say, hey, you outsider, don't bother about our internal matters. We are secured, we are guarded, we are protected, and this is all that we can give to you. This is what happens, right? So when you write the equation of motion for M1 and M2, given the external force, the internal force will have no role to play. But in the free body diagram of M1, the internal force will find a place. In the free body diagram of M2, what M1 is doing to M2 will find a force. But together, the internal forces will find no representation. That's the key thing. And the obvious fact is then, suppose this is M1 and this is M2, and the net external force acting on the system, it's not like a physical boundary. Say the net external force would be the resultant of this F01 and F02, and say that was something like this, F external. It could have been acting on M1 alone or M2 alone or a combination of M1 and M2, right? And suppose this M1 has an acceleration whose component in a given direction, say, is A1d. Its acceleration in this direction is A1d. And in the same direction, the acceleration of M2 is A2d. These are components of the acceleration of m1 and m2 in a given direction d. They are parallel, right? These are not the total accelerations of m1 and m2. a1d is the acceleration of m1 in a given direction. a2d is the acceleration component of m2 in a given direction d. They are components of the total acceleration. And then suppose the component of the force in the direction d is F external d, is the component of the force in the same direction. Then in this direction, if I have to write a scalar equation for Newton's second law, then F external in a given direction. What is F external in a given direction? That's a component of the net external force in a given direction d. And what does it do? That's like m1 into a1d plus m2 into a2d. And this is a scalar equation. Realize it's a scalar equation. This is the component of the external force in a given direction, which is a number. a1d is what? Component of the acceleration of m1 in a given direction. a2d is the component of the acceleration of m2 in a given direction. And this is second law applied in a given direction. This is second law applied in general for the total acceleration of a1 and a2 of masses m1 and m2. But this is in a given direction. You resolve F external, you resolve A1, you resolve A2, then that's second law applied in a generalized second law applied in a given direction. So which means now this in general is generalized second law of Newton. Newton's second law. Generalized Newton's second law. And in a very general sense, there could be n particles, all mutually interacting. Then the net external force, if there were n particles, would be m1 into acceleration of m1 plus m2 into acceleration of m2 plus mn into acceleration of mn. That's generalized second law for a system of n particles mutually interacting. Each pair of particles could be exerting a force on each other, but doesn't matter. Right? All's good?